So, hello, everyone. So I would like to welcome to our public lecture today. I'm Andras Rashi, the chair of the mathematics department here at Stanford. And we are delighted to start up our public lectures again after this hiatus due to the pandemic. And we, of course, a little bit out of practice, so we tried, and also the university is suffering from a serious classroom shortage of any kind, even after 5 p.m. So we tried many days, and finally we found this, and we managed to find this room. Unfortunately, we managed to find on a day that coincides with all our calculus midterms. So I'm sure. But we are gaining practice again, so hopefully in the future this will go a little bit better in terms of timing and classroom finding. But we do need classrooms, or even our dean has trouble finding a room for something she's trying to organize. In any case, apart from such organizational troubles, it's really great that finally we have these lectures, public lectures back, and also to start with such an outstanding lecturer. So our lecturer today will be my friend and colleague, Ravi Vakil, who has been at Stanford for a few years, just a few more years than myself. He's an amazing research mathematician as well as educator and lecturer. And thus, in my opinion, is an amazing choice for this lecture. So to indicate this, some of his honors include he's a Simons Fellow, he's a Fellow of the American Mathematical Society. He has received an André Eisenstadt Award from the Centre de Recherche Mathématique, a Presidential Early Career Award for Scientists and Engineers, a Frederick Terman Fellowship, a Sloan Research Fellowship, an American Mathematical Society Centennial Fellowship. So this is on the research side. On the education lecture side, he is a Bass University Fellow in Undergraduate Education. He's received the Lester B. Ford Award of the Mathematical Society of America for his article actually on Doodling that we will learn more about. Well, I'm not sure exactly what the overlap is, but we'll learn that. A Poya lecturer. He has received the Dean's Award for Distinguished Teaching and many other things. So Ravi, in addition to being such an amazing mathematician in many different ways, is an excellent doodler, as we'll hear today, as well as he introduced various new concepts such as Murphy's laws to algebraic geometry, and very much hope that this won't apply to the lecture today. But please let us welcome Professor Ravi Vakil.
Thanks. Let me just check whether, good, it works. Thank you very much, Andras, for that kind introduction. Let's hope I will stay away from this, or it might. I might get some feedback. Great. So thank you very much for coming out tonight. And what I want to tell you about is, on one sense, just doodling. So everyone doodles in their own particular way, and I'm going to try to tell you a little bit about the way in which I doodle and some of the mathematics that I later realized that I was connected to. And I think what I'm going to do is going to look like play. But in my mind, and the case I want to really make to you tonight, is that this is what mathematics and maybe what pure science is really about, which is about finding patterns out there in nature. You look at nature, you notice something, and you can't help asking yourself certain questions, and then you try to explain them and then extend them, and that leads you to new questions and new understanding. So in school, sometimes we're told that mathematics is about finding answers to questions other people give you and then answering them. But really what is tricky about doing mathematics and about doing science is finding out what the right questions to ask are. It's easy to ask questions that have no answers or answers or that are difficult or impossible to answer. And you want the sweet spot where there are questions that no one knows the answer to, but they're within reach and there's some magical idea that will actually get you there. So I want to do that today by trying to find interesting questions buried in everyday doodles. So you should see this as some sort of model of how I think we should look at the world with some sort of sense of wonder and curiosity and wanting to figure it out. So there's going to be a lot of room for exploration. Some of the answers to the questions I say are going to be quite sophisticated, but there are a bunch that I don't even know what the answers are. And the questions I want to ask are going to lead to a bunch of mathematics and a bunch of different fields that are really, I'm not an expert in myself. But that's, in some sense, why I became a mathematician, why I'm interested in science. And I think it's what being a mathematician is really about, and being a human being is really about, which is about willing to be seriously curious about something you aren't an expert in, and to push your understanding and not restrict yourself to safe areas where you know a lot. Okay, so I'm going to get to different things like Hilbert problems, Fields metal work, current cutting edge research, but I want to begin somewhere simple. So, okay, but before I start, I just want to say, because he passed away very recently, the person who early on in my life kind of taught me to think this way was one of my favorite teachers in school. This is him when he retired. It's kind of a very typical picture because I see lots of grown-ups, but he's hanging out with the people with his people who are all very short. So I think of him when I think about these things. Okay, so let me begin by telling you how I doodle, and then I'm just going to start to ask questions about it and see where we go. So you saw it at the front page, but basically what I would do is you're sitting somewhere, maybe in a math lecture, and your hands just start doing things. And so my doodle is I would try to draw a line, draw a little curve as close as I could to some shape, maybe a word, and then I would do it again and again and again, and I don't need to tell you why. Well, I don't need to tell most people why it's aesthetically pleasing to do things like this. It's very satisfying aesthetically what gets produced, and there's sort of a reason for it. So one thing I want to make clear at the start is that I'm not contriving this just because so much is going to come out of this. You might think that I'm making this up. So I want to just quickly do a quick poll. How many people in the audience have doodled like this in the past? Like just something like this. Okay. So if your hand's not up, you're the strange one. Okay, so this is really something out there that we do. It's not made up. And so I used to do this when I was even, as long as I can remember, certainly from when I was around age 5, I would draw like this. And then you can't help but do it and wonder things as you're doing it. And I guess the way I would think about it when I was very small is that when you keep on doing it, they get rounder and rounder. They look like balloons blowing up. They become more and more circular. And so that's the question I asked. And when you're 5, you just ask questions, and it's a good thing to do. And I didn't have an answer, and I just let it go because when you're 5, you don't have many answers. But it stayed in my mind always. So it was only much later that I ended up thinking more about it. So okay, so that was a question I asked, but there are many other things you could ask about this very strange thing. I'm just going to start with this very simple doodle. I'm just going to start here, and maybe just to get us into some sort of mood of how these things translate into formal mathematics, and why you shouldn't worry about it if you're not comfortable with formal mathematics, is this, which is, before I get going, I need to figure out what I'm talking about. So there are phrases like, I don't know what more and more circular mean, for example, and so we need to figure out what that means. And I don't even know what doodling means in some formal sense, but I can still ask the questions. The questions always start out fuzzily. So let me say precisely what we're doing. So here's one possible description. And you might have your own description that'll be similar or maybe the same. So I'll say it this way, which is we've got some shape. So for example, you've got this shape. Let's see if this works. Good. It does. So you have this shape I've written down here called x. And what I want to do with my doodle, I'm going to think of it as all the points that are close to x. So let me do it this way. So I'm going to think of all the points that are kind of close to x, that are within distance r of x. So I'll call that something that I might call the rth neighborhood, all the points that are kind of within r, that I can get to within r of x. And just because I need language for it to talk about it, I'm just going to use a symbol. So nr of x just means that neighborhood. And I picture like a dust cloud around the shape. And then if you want to impress your friends, you can say it formally like this, which is the rth neighborhood are those points that are distance at most r for some point in the original shape x. But just, I'll never show you that again, but I put it there just to say that the symbols are nothing more than what I said in English before. So it's just a language with some sort of embedded logic. And now that I've said it, I can now reword my question and sound fancier, but really say the same thing, which is I'm going to start with the shape x, and I'm going to doodle around it. Maybe let me do it this way. So I do one doodle around it, and then I do a doodle around that. So that's that shape. And I keep on going, and I do it again and again and again. And it gets my question then, my 5-year-old question, which is now sounding fancier, does it get more and more circular? And I still don't really know what this means, but I already want to point out something that the 5-year-old, the ... the doing it again and again and again, is the notion of a limit, which you're not supposed to talk about until you're in high school. But it's something that you understand when you're small. You understand the phrase of do it again and again and again, and something happens. So what's hard about limits is not the idea. It's something else about limits, which is making them concrete and saying things about them. But absolutely limits, when you're 5 years old, you know about the speed of a car. And that means you have a good sense of it. Your intuition is already correct. Okay, so I have a question now that still doesn't make a lot of sense. But let me, I want to make it make sense. So let me ask another question in advance, which is, then this suggests, because I've got this symbol, when I write down the rth neighborhood, well, there's a size of my doodle. And so you could ask yourself, how does that make any difference? So for example, I could do a doodle of size 2 around this shape. And if you instead, you're more coordinated, so you could do a doodle of size 1. Well, obviously, I can say how they compare. Your doodle is inside my doodle, because it was a doodle of size 1. So let me make it more interesting. Let's do 2 doodles of size 1. And instead of 1 doodle of size 2. So now it's harder to say. How do they compare? So it's something you wonder, and so you can have an opinion on it, and I'm going to ask what your opinion is on this. And now I want to, okay, let me tell you right now, I'm going to take a vote soon on what you think. So whether you think that if I do 2 doodles of size 1, if you think it's at least as, the big green one is at least as big as the red one, or if you think 1 doodle of size 2 is going to be at least as big. So I'll let you think about it a bit before I tell you to vote. But let me tell you why I'm doing this. Because when you could wonder about it, but you can't make it's something psychological about the fact that you need to have an opinion, and there's nothing wrong with your opinion being wrong so long as you're willing to change it when confronted with evidence. Yeah, so you should not be afraid of having an opinion, and you have to have skin in the game. It's the reason when you do an experiment, you need a hypothesis. You don't just say, you don't go into a chemistry lab and say, I'm going to mix these chemicals together and see what happens. You have to have a purpose in what you're doing. You want to test something, and you don't. And so I want you to test your intuition, and then if you're wrong, you can improve your intuition. And if you're right, you'll also have learned something. And the other thing I want to say before taking the vote is that really this is something then, if you're unsure, and before you try to prove anything or do anything fancy, you could imagine measuring it. This is writing a computer program, taking out a ruler, taking some string. So the other thing is that this is, in some sense, very abstract and pure, but pure mathematics is an empirical science. It's something that you get your hands dirty with. You have to understand the world. You have to try things out, see what works, see what doesn't work, before you get that better understanding. Okay, so now I'm ready for the vote, and now hopefully you've decided, and you're not going to change your vote based on what other people say. So my question is this: who thinks? So let me just tell you the question again. The choice is I start with one shape, and I do a doodle of size 1 and another doodle of size 1. That's the big green doodle. Or I can do one doodle of size 2. Do you think the green one is at least as big, or the red one's at least as big? I don't know if you have any questions before we vote. Any questions before? Okay, great. Who thinks the green doodle is at least as big? Raise your hand. Okay, who thinks the red doodle is at least as big? Raise your hand. So it looks like now the greens have it, but it's pretty close. I'd say it looked to me like maybe 60% voted for green and 55% voted for red. Okay, so let me just check. Who didn't vote? Raise your hand. You're wrong. So you're guaranteed to be wrong. So if you don't have an opinion, you're guaranteed to be wrong. So okay. And so who voted twice? Okay, this is the Chicago rules voting. Okay, so if you voted twice, so now everyone except for those people who didn't vote, and the people who didn't vote even when I asked whether they didn't vote, everyone who voted was right. In fact, and the people who voted twice were right twice. In fact, the answer is that they are exact. I thought someone was going to ask me what I meant by at least as big. But once you wonder this and you test this, and then you had a computer program or you be very careful, you notice that my drawing isn't so good. And if you actually did it, the red line and the green line would exactly overlap. And that can't be a coincidence. So you ask the question and discover something, and there must be a reason for it. So that's the next question, which is, in fact, you guess, or you want to say conjecture, that these two things are the same. So there's something we want to understand. And then, so what is now we have discovered something new, which is that we are expecting this to be true, then be exactly the same shape. And so in the course of showing this, actually let me go one more thing, which is something with experience, not that it matters too much what's going on, and what's going to happen is that you realize what mattered about the 1 and 1 and the 2 is just that 1 plus 1 equals 2, and you should expect something better. So if you take a doodle of size B and then a doodle of size A, you should get the same thing as a single doodle of size A plus B. And that's like an empirical fact that you just play with and you believe it might be true, and you want to know why it's true. And so when you try to understand why it's true, you led to one of the most important facts in all of mathematics, which is something that, again, I think a 5-year-old, but maybe a 10-year-old would know, not by this name, that you would have seen before, not by this name, no matter who you are, which is the triangle inequality, because you know the shortest distance between two lines is, between 2 points is a straight line. And so in particular, if the shortest distance between, if you're trying to go from point A to point B, that's the way you want to go, and it's going to take you at least as long if you go by way of point C. So mathematically, I'm just saying this: the distance from A to C plus C to B is at least as big as A to B, and that certainly the only way it'll be just as long is if C happens to be on the road between A and B. So in the course of, so let me bring this back to the question, but you'll see that in the course of just doodling and asking this question, we would have been inevitably led to discover this inequality. And now comes the explanation as to why when you doodle twice, do a doodle of size B followed by a doodle of size A, you get something the same as a doodle of size A plus B. And so how do we show this? Well, we basically go back to the vote, and we show that both sides of the vote were correct. So the people who said that if I take a doodle of size B and then a doodle of size A around that, it's at least as big. Well, what does that mean? It means that anyone, if you take a big step of size at most A plus B, like that the green person thinks that they can get there with the step of size at most B followed by step of size at most A. And certainly they can, because they could just break this up proportionally into 2 pieces. That's very believable. And now how about the red person? Well, the red person, they think that anything that the green person does, taking a step of size at most B followed by a step of size at most A, they think they can get there in a step of size at most A plus B. Well, how do they know that? That's the triangle inequality, because the shortest distance between these 2 points is a straight line, so it's got to be faster than that. So in fact, this fact is equivalent to the fact that the triangle inequality is true. If you try to doodle on a ball, on some other shape of any sort, no matter how complicated you try to make the question, this is all about the triangle inequality, the shortest distance between 2 points being a straight line. Okay, but let me go back to the original question, which is I wanted to take a shape because I'm 5 years old and I'm bored, and doodle and doodle and doodle a million times, or even a gazillion times. So there it is. I can doodle a gazillion times around my shape. But now I know that rather than doing it repeatedly, by taking all this and doing it a million times, I should instead just do a single doodle of size 1 million and cut out the middleman. So that I know I'm going to get the same thing because I've checked that that's the way doodles work. I can just do one single big doodle. And now I can ask my question, which is, as this gets really big, I do a really big doodle, does the doodle get more and more circular? And the answer, and now the answer is going to be yes, and I'm going to tell you why, and I'm going to tell you something, and I think this is the hardest thing I want to try to say, but in this hour, but I hope it's early for me to say it, but I hope you stick with me because it's actually not so bad if you just see it the right way. So here's the principle, which is if I've got a shape inside another shape, A is inside B, if I were to doodle around the first shape, then and I doodle around the second shape, well, the first doodle's got to be inside the second doodle. And that's true. I can make a bigger doodle. And so why is that true? Well, what I'm saying is any point that is close to A within R of a point in my first shape is also close to a point in my second shape because everything in my first shape is in my second shape. So let me say that again, and I'll see if I got that across. And I'm hoping that maybe a majority of you will be OK with it, and the rest will just be willing to accept it, which is that you have a shape inside another shape. Let me do another picture here. And I'm going to do the same size doodle around both shapes. But now I'll make it, my doodle is going to be pretty big now. That's my doodle around my first shape, and that's my doodle around the second shape. And I say that the first doodle is still going to be inside the second doodle. And that's just because these are all the points that are within R of this shape. And these are all the points that are within R of the bigger shape, so it has to be somewhat bigger. So I want to maybe nod your head if you can kind of see what that's doing. OK, so I think I've got my majority, and I'm also happy with you semi-pondering it more later. And now I want to do something to answer this question, but then I'm going to go back to a question from when I was 10. But this is the nature of things. The questions you ask when you're 5 are the hardest questions, and they get easier and easier as you get older. So here's the idea. And so we have a shape X, and I'm trying to. And the question is this: there's my shape. If I do a doodle of size 1,000,000, which I can't do on the screen because 1,000,000 is way bigger than the screen, does it look really, really circular? So here's my idea. What I'm going to do is I'm going to start with a point inside. Let me call it P. And I'm going to think about circles centered at that point. So for example, here's a circle that contains X. So I've got a point inside and a circle outside. So that's what this means here. I've got a point contained inside X in the circle. And now I'm just going to doodle around all three things. So I'm going to take a doodle around a point. There's the thing I care about, the doodle around X, and then doodle around a circle. So when I doodle around a point, what shape do I get? A circle. So I get a circle. When I doodle around the circle, what do I get? Another bigger circle. OK, so we have two circles. And then I don't know what I get in the middle, because I still don't know. But now all I know is that this doodle is kind of wedged between these two circles. So let me just draw you a picture. So my picture, when R is 1,000,000, and let's say S is 1. So let me draw a circle of radius 1,000,000. There it is, seen from far away. And now I'm going to draw you a circle of radius 1,000,001. This is not to scale. OK, that didn't quite work, but good enough. That's not to scale. And then the actual doodle's border is somewhere in between. And now you've got to admit that looks really circular. And so when R gets really big, which is I can use calculus speak or 5-year-old speak, it means that this red boundary is wedged between these two circles that are so close to each other you can't believe it. And that means, and you could say this in a fancy way if you want, and some people will recognize things like the squeeze principle, but for sure you see what I mean, that you have between a circle of radius a gazillion and a gazillion 1, then surely if the borders between the two, that counts as being more and more circular. So now, what do? Now I just declare victory. Clearly, that means more and more circular. So I say that's what I meant to begin with, and now I'm done. And now you might think I'm cheating because I told you what I meant only at the end of the argument. But that's actually how science works. You actually have a vague idea, and it only becomes precise what you actually mean when you actually finish, when you have finally some sort of understanding. So. OK, so if you think that's a cheat, wait till you see what's going to come in a second. Okay, so now a question that I saw about probably when I was, maybe even when I was in the class of the teacher I showed you, Mr. Long's class. And so here's a question I heard, and so it's the following question, and a number of people in the audience might have seen this in some before. So you take a convex polygon. All that means is, look, that's a pentagon. It's got no dents. So that's my picture. Consider that pentagon, and it's got a perimeter. And actually, if you measure that carefully, you'll notice the perimeter is 4. And now I tell you, the perimeter is 4, and now I'm going to doodle around it of size 1. And then my question is, how long is that doodle? A very natural, basic question, which is I just doodle. How long is that doodle? And now you might say, well, okay, you told me it's a pentagon, and I know the perimeter is 4, but how long are the sides? What are the angles? And I'll say, there it is. Decide for yourself. And so my question is, what is the answer? And what's interesting, what I'd like to do is get a guess for what the answer is, possibly from someone who hasn't seen this before, and possibly from someone who's like under the age of, younger than Andras, perhaps. But, well, okay, so yes, question, idea? Yep. Is it so it looks like the question is it so you think it doesn't even depend on the shape of the pentagon? It sounds like I thought you measured it very carefully. Yeah. So you're right. It doesn't depend on the pentagon, and it's not exactly 5, but it's something. It's some constant. And now so you said 5 because you're thinking. Can you say what went into the 5? Like why did you say 5? Yeah. Right. No, but don't laugh, because he actually had a better idea than any of you, and it leads exactly the right direction. So it's like, right, so it's at least 4. It's bigger, he added the 1, and where did it come from? And so it's got to be at least 4, and the final thing has to have the 1 in it. So okay, good. So based on that, I think you led more into, fire away. What's your? Bits of the corners. Like that, like the curve. You're complaining about my drawing. Okay. Like that? Okay. Okay, that's okay. So now what? Okay. Okay, so now I buy, okay, so what you've just said is you told me to draw much better, and you made me draw some rectangles. And now I believe this 4 is visible now, because this is this. So because it's a rectangle, this thing, you can see this edge going all the way out to there, this one going out there, this one there, this one there, this one there. And so now, so it's 4 living on in this new thing makes all the sense in the world. And now and what's changed? What has he added in? Or what have we added in? Only this bit here. And the question is that it's not 1. So what is this thing here? 2 pi. Why? Who said that? Why is it 2 pi? So now that this has been improved to 4 plus 2 pi. Lucky guess. No, but why is it 2 pi? Circumference of the circle. Right. So in fact, these pieces, I don't know what that angle is at all. I haven't told you what they are, but you can slide them all together, these 5 pi pieces, and get 2 pi. There's one piece. Okay, now I'm really drawing poorly. Hopefully you know what I mean. The green things turn into 5 pieces of pi that all slide together, and there you go. And the circumference of the circle, it turns out to be 2 pi. And I should say you could have done something for people who remember their grade school math. There's like something called the exterior angle formula, and you could use that here too. But actually, what you've accidentally done in proving this is you can actually prove the exterior angle formula too, like all sorts of things. And where did it come from? It started from the guess of 5, and it should be more than 4, and then you have to add some more stuff in, and then you refine. So people who are afraid to guess are guaranteed to be wrong. And the people, okay. And the great thing about this is once you see this picture and suddenly you have understanding, and you know you can answer something else as well. So let me ask the question. Let me just first say let me see if I can fit this in. So the perimeter, the new perimeter is the old perimeter plus the circumference of a circle. And I should say, and I have a picture of of a racetrack. And I should say that that should look like a doodle, and it's not a surprise. And if you've ever wondered why things are staggered and how much they're staggered, I won't say more about this here, but this makes you think about how this relates to what we're talking about as well. But now I'm going to go in a different direction and ask another question that you could ask at about the same time, which is what's the area of it as well. So I'm going to tell you something. If I tell you the area of this pentagon, what's the area inside the entire doodle? And now you can just look at this picture and see that it's the original area. That's the middle. So I can break it up into pieces. There's this piece in the middle, which is the original area. Then I see these rectangles. That rectangle is the side times r, side times r, side times r, side times r. So I get the perimeter times r. I'm doing this terribly. Area plus perimeter times r. And then these bits of a circle, pi r squared, exactly, pi r squared. And there's the, so as usual, we get something that's like a bonus fact as well. And then when you're older still, now this is only for people who, and this is only for a second as an aside for people who remember their calculus, that you can't help but notice that the derivative for people who remember their calculus, that the perimeter is the derivative of the area. And that can't be a coincidence for any, so the question is, why is that true? And I'm not going to, I mean, now we're getting into deeper water, so I'm not going to tell you, but it's just more like this is the kind of question that's there, it can't be a coincidence. And so the point is that we're inevitably led into these insights, and that you really, once you start asking questions, you have no choice but to start discovering these things. And so let me try to say something in a different way, which is if you look at the area of the doodle, then depending on the size of the doodle, it's a polynomial where you have like an r squared, you have an r and a 1, and the coefficients of this polynomial are things that mean a lot. Like the area is geometrically meaningful, the perimeter is meaningful, pi means a lot in geometry too. And so that's something, this polynomial is trying to tell us something. Okay, but now let me generalize. And now let me say that, okay, so now let me say that Rx has no dents, but it's not a polygon. So I don't need to define it. I'm going to define it. It's a picture. It's not like, it doesn't have nice straight edges. It's round. It's not a nice round. It's a weird round. It's round like this deflated ball, but it's except that it has no dents. And I want to do the same thing. And so let me make a redefinition a bit, which is, the way I'm going to do it is I'm going to walk around, my doodle is going to be described as follows, which is I'll walk around the boundary of x counterclockwise, and if you measure my arm, its length exactly r, and so I'll mark in pen, and that's my doodle. And my question is, what's the perimeter and what's the area? And now the question is, let me just leave it as an empirical question, because you can imagine measuring it with a piece of string, or measuring it with, or writing a computer program to estimate it. And it turns out that you'll discover, and you'll wonder why it's true, that the same formulas hold. And now the argument you gave me before all involved all these straight edges. And then doing like these things with circles. You can't do that now. Your argument makes no sense. And yet it still works. So and it's a great, like you do an ellipse or do some shape, you know its perimeter, you do a doodle, you just know for sure what the size of the doodle is. So the question is sort of how can something which you want to make this work with the straight edges, how can something that feels so right be so wrong? And so to make this make sense, you could do one of two things, and both of them, depending on who you are, like which one you like better really tells something about who you are, which is if you are one kind of person, you go to college and you take calculus and you learn about Green's theorem and you can use it in a very clever way to prove these formulas. Another thing you can do is you could say, well, I really like that argument. I really wished it worked. And then you try to make it work, and you wave your hands a little bit. And is that worse or better? Because what you're doing is you are following in the steps of Newton and Leibniz in inventing the calculus. This is exactly how they were thinking. They were not thinking by invoking Green's theorem from a line in a textbook. They were thinking through, that using their intuition, how to define things correctly. And maybe it wasn't the fastest way, but it was the intuitive, really the right way through. So this is the way in which you're led into steps, led to sort of follow in the path of the ancients, not by trying to imitate what they did, but try to think the way that they thought. Okay, so let me take an aside for a puzzle I heard again when I was about 10, which is also related to this. And so I don't know what it's called, so I'll call it the string around the earth puzzle. And so what it is you take a sphere. So, okay, I don't know if you can see this is a sphere. I didn't inflate this, so I can't use this as an example, sadly. So imagine that you take the earth and someone puts string around the middle and then cut the string, add 1 meter of string to it, and then glue it up again, so it's a loop, and then levitate it off, so it's like the rings of Saturn. And my question is, how far is it levitated above the earth? And the answer, I said, okay, I'll take the answer in just 1 second while I point out something. Or is it a question or an answer? Answer, good. I'll hold off on the answer for just a sec then, just to make sure the question is clear, which is, you may wonder, okay, obviously, this is not the size of the Earth. Or if you don't know that, you've got more serious problems. So obviously, you want to know the size of the Earth to make this work. So you may ask me, okay, how big is the size of the Earth? And the answer is, like, you live here, you should know. So he knows. You can ask him. So great. So what is the answer? At the gentleman at the back. 0 meters. 0 meters. What's that? Oh, you're rounding to 0 meters. Great. Okay. Ooh, that's good. Great. Okay, good. So that is indeed correct if you're rounding. Let me take a vote then, since I agree it's a small number. And the question is, how small is it? Is it closer to a millimeter, 10 to the minus 3, or a micrometer, which is 10 to the minus 6, or a nanometer, which if you look is 10 to the minus 9 meters. So I agree it rounds down to 0, but how small is it? So now I'll take another vote. And the good thing is you can't all be right. But if you don't vote, you're guaranteed to be wrong. So, okay, so now just take a guess. A question? Or you're already voting? A question? Sorry, what was the question? All right, how many meters is it? Right, so I'm deliberately not telling you, which is messing you up. Although maybe, if it helps, you know I'm a pure mathematician, and so that means I probably don't know the answer, which means it probably mysteriously does not even depend on the, so the miracle is going to be that it does not actually depend on the answer to that question, which is the amazing thing about this question. So let me make it up. The Earth is actually 100 miles around. You're laughing. Okay, something. Okay, what's so funny? Okay, so.
40,000 kilometers by ancient French standard.
Oh, good. Okay, by ancient French standard. Great. So if you change the miles to kilometers, it's 40,000 kilometers. So great. So do you think the string is closer to who thinks it's closer to a nanometer? Raise your hand. Who thinks it's closer to a micrometer? Raise your hand. Who thinks it's closer to a millimeter? Raise your hand. So a lot think millimeter. Okay. And who didn't vote? Okay. So you're guaranteed to be wrong. Okay. You know you're wrong. You knew what was going to happen. and it's true that it's not exactly between two. So only one of the three is right. So the amazing thing is it's actually more. It's actually pretty. It's about this high. And let me say why it's true, because it actually is secretly a question about doodling. So if you look from above then and see what it looks like, there's a string around the Earth. It's a doodle around the Earth. And so the length of the string, the perimeter of the doodle, is the perimeter of the Earth plus 2 pi r. That's the thing which you came up with. That means if you add 1 meter of string, you start off with this much string, and you add 2 pi r, you add 1 meter of string, that's what you're going to get. So that means the height is 1 over 2 pi meters, and it doesn't matter how big the Earth is. And better yet, like so that's the thing you get when you're 10. You don't do it this way when you're 10. You use the fact that you actually have to think about the size of the Earth. This is not the way you would normally do it. But the cool thing then is once you see things that are fancier, you realize you don't care that the Earth is not a sphere, because it works always, because the doodling thing we're working didn't require it to be a circle. So it works even if the Earth is kind of lopsided, or like it looks like Mars is a different size, or even like a lumpy asteroid. like that, when you wrap string around it. It always works. It's always 1 over 2 pi. Okay, so let me say a couple more things related to this, which is, okay, so let me do this again. Let me generalize, because what you always want to do is take what you know and push it beyond what you actually know. And so I'm going to take my shape. It's now going to have a big dent. So I'm going to give up. So there's my shape x, and you can see it here. It's got a massive dent. And now I'm going to walk around the outside and doodle, and there's my doodle. And I'm going to say, what's the length of that doodle? And so just to be clear, the length of the doodle is all of this. And then you ask your computer programmer, you take out your string, and amazingly, you get the same formula for the perimeter. Maybe, I don't know if that's amazing or not. And now, I'm asked the same question about the area, and now what do I mean by area? So I don't mean everything like this. That would not be the right thing to do. I might reasonably mean this thing, the donut minus the hole. So I'm not sure what I mean. So what I want to say is, if you give me the right definition of area, and I'll give you the right definition of area in a second, then this formula holds. And if you don't give me the right definition of area, this formula doesn't hold. And so the answer, maybe someone will quickly say, what's the area? What is the? Maybe my question is not clear, so I don't know if I should ask it. What does the area of this thing want to be? I feel like that's not a fair question because I'm not sure. What I mean to say is that you need to double count this bit. It wants to fold over itself. So if you double count this and you check what the area is, it is this formula. So this is the way I would say this. The area wants to be this. Nature is telling you what the definition is. If you think the area is something else, you're wrong because you never argue with nature. And if this looks like a dumb thing to say, think about mass and weight before Newton. There's one notion about how heavy something was. And after understanding nature better, we learned that it made sense to distinguish it into two separate meanings. We changed our definition after thinking carefully. Well, it wasn't me, it was Isaac. But we changed our definition and we bifurcated into mass and weight. So to test this out, I'm going to give you another example, which is a figure 8. And I'm going to walk around the figure 8. And there's my doodle. And then you measure the perimeter, and it turns out you get a different formula for the first time. The 2 pi r has gone away. So that's already a mystery. And the second thing, but just to I'm going to give you a riddle to think about, is that what's the area? Well, with the right definition of area, you get a nice formula. It doesn't have a pi r squared, but it's a nice formula. And if you have the wrong definition of the area, you don't get a nice formula. So area, the figure 8 wants a definition. It's telling us what its area wants to be. So what's the definition of the area of a figure 8? And the answer is not this area plus this area. It's something else. And so all I want is a guess, and I'll tell you whether it's right or wrong, or if it's higher or lower. Because if your guess is wrong, you can always edit your guess. This is a good thing about trying to figure out the universe. So what does the area of this figure 8 want to be? And I'll tell you that if you say it's this, you don't get a nice formula. You get something which is way bigger. What was the top? Can you say it again? Top minus the bottom. In fact, that is right. So you take this area and negative of this area. So this figure 8 has negative area. And that is a correct, now of course you need a proof. But that's the right definition. And if you take that definition, it turns out this is true. And so now we'll worry about later why this might be true, but you know he's made the right definition because it empirically is nice. The world is beautiful with that definition. The world is horrible with the wrong definition. So great. And then there's, of course, the question of how the formula changed. So let me ask about the question about where it changed by experimenting a bit further. So here's another shape. I'm going to walk around the outside, and what happens is it loops around itself. So there's my doodle. And if I check out the length, I don't get a 2 pi r, I get a 4 pi r. And when I work out the area, I don't add a pi r squared, I add a 2 pi r squared. So you could just imagine writing a computer program to check each of these. Oh, but what is the area? Okay, the perimeter is right. The area is you need to double this area. So there's some mysterious rule where you've discovered area with multiplicity by just asking this question about doodling and trying to understand what area could possibly mean. And now I will just, because this is so rich and I could ask you interesting questions, but I'm just going to tell you the answer about this, that what is this, where does the number come from? 2, how did it change from a 1? It's a notion of winding number, a notion from physics when you run electricity through a wire. Or I can put it differently, that if you were to watch me walk around the outside of this, of the shape, if it was on the ground, I would appear to turn around twice net. And that's what the 2 is. So this is notion from physics, if you want, or some sort of topology that we end up discovering by trying to figure out, even just trying to just do doodles and seeing what happens with the shapes. And if you doodle in geography, so that's a picture of Hawaii when I was there. I guess that's the Big Island. So the people always laugh at me when I talk about the real world for some reason. But okay, so when you doodle around Hawaii, it's got lots of like lakes and islands and things, and like the palm trees don't affect the doodles, but they're palm trees, and so it turns out that once again you get, now this is something which I only realized later on for reasons that you'll see, that you get the old area is the area is the area plus the perimeter times r plus some mystery integer times r squared. It's a different integer. This mystery number is what's called the Euler characteristic, which is the notion in topology that you normally only see in a graduate, typically wouldn't see before you take like a graduate course in a PhD program. And yet, when you just do this if you just do this if you just do this and ask the question of how long does the seafront change when I do that, or if you want to be depressing, you could say with global warming, if the water rises, how much does it go? How much does it go down? You will discover the Euler characteristic, and sort of forced upon you by this doodle. Okay, so let me now keep trying to generalize things more and more and more. So let me ask something about, so a standard thing is you like thinking about different numbers of dimensions. And once you can expand your brain to think about above 2 dimensions, or ideally even 3, you want to generalize it. And then you want to go to any number of dimensions. And if you're really ambitious, you want to do that. But I really want to say, as an aside, you should really try to generalize to 1 dimension and try to figure out what doodling means there. And that actually is strangely confusing and enlightening. But let me just go with the 3-dimensional question. And so what does doodling mean in 3 dimensions? Well, think about it this way, maybe. Like, think of it now as like a dust cloud. So I've got my shape in 3D, and I have a dust cloud of all the points within like 1 unit of this box. And let's just work out an example of how big let's do the volume of the dust cloud around this box. So this box, well, okay, how big is a box? Well, if you measure it, the length is actually L, the width is W, and the height is H. And so let's work out the volume of the doodle around of the dust cloud. I picture like Pigpen and Charlie Brown. So like if you've got this dust cloud around it, what's the volume of the dust cloud? Well, in the middle of the dust cloud is the original box. So there you go. There's the original. So that's what's my last line. My volume of the dust cloud is the original box, and then on top of the box we've got layers of dust of thickness r above this and above this and above each of the 6 faces. So that's the surface area times r. And oh yeah, there's still the things like the circles. So there are these octants, little octants of spheres in the corner. So we get plus 4/3 pi r cubed. So we get a nice simple formula like that that we would try to generalize. Okay, sound good? Okay, so now let's, actually everyone is, some people are smiling again. I don't know whether, so does it really sound good? Yeah, it really sounds good. Okay, now you're I don't believe you that you think it sounds good. So in fact, I'm lying. And you're believing me too quickly. So in fact, it's easy to make a mistake. And there's some clues that I made a mistake. And there's one term which is somewhat, so what did I miss out in my dust cloud? There actually, if you think about what I described, there are pieces in this 3D puzzle I missed out on, which are like quarter cylinders around, like bumpers, if you've ever had a baby whose head was magnetically attracted to sharp edges, around each of these things, and each of them is like a quarter cylinder, and so when you put them together, you get this extra term, pi r squared times L plus W plus H. So it's the one that everyone misses. In fact, when they try to think of it, and I think there's like some moral, philosophical reason why it's a tricky case. Okay, so we try to do this great. So we'll try to do the same thing. This should generalize. So we should try to do this with various different shapes. So with a sphere, okay, it's not a sphere, but with a sphere, it should be what? The original volume plus the surface area plus r times r plus 4/3 pi r cubed plus, wait, what's length plus width plus height of a sphere? Well, I guess there's maybe a reasonable guess, but if you try it out and work out the volume of the dust cloud, you just get some mystery term there, something times r squared. Or if you try it with a weirder shape, and you're very clever, or you write a computer program, you would get v plus ar plus 4/3 pi r cubed plus some mystery things times r squared. So there's something new going on. And I should say, for super experts, the case of a torus is going to be I'll leave separately to guess this, if you can guess what's happening here. So something is happening here. And so what it means is that if you believe in 3D, the notion of volume is important, which is like, that's a fundamental notion. Surface area is a fundamental notion. The unit sphere is a fundamental notion. Then there's some fourth sister in the family that must be really important that we are not. It definitely is on the same footing as the other three. And we don't even know how to, at least right now, as we discuss it, we don't know how to define it for a weird shape. So the question is, how do you define this mystery new invariant, this mystery new thing in 3D that you wouldn't know, that didn't turn up in 2D? Okay, so I'd like to tell you about this, about one of my favorite problems of all time. This I heard when I was about 18, because I definitely remember when I heard it, because it was so cool. It's a problem. It's a Russian problem. I've heard arguments as to whether it's from St. Petersburg or from Moscow, and I know people get very head up about that. So I will not. So I'll say there's like a train company that goes between St. Petersburg and Moscow, and the rule on the train is that you're not allowed luggage boxes whose length plus width plus height exceeds something like 1 meter. And the question is, can you, so actually before I go on with the question, you'll think this is like a made up kind of thing, but okay, here's a boarding pass from a recent flight I took, and the rule for carry-on luggage is exactly length plus width plus height. So they are using this weird version. So this did not come from nowhere. And you're welcome to look at the boarding pass after. It's a United boarding pass. These are the rules. I don't make them up. And the question is, can you cheat by taking, so you have one box, and it's illegal, and it's illegal, but maybe you can put it in another box that's legal. And now certainly, if you can't fit it in nice and perfectly corner to corner, because otherwise then the 3 dimensions of this one will be smaller than the 3 dimensions of that one. So if this one is already illegal, that's illegal too. But maybe you could fit it in some like slightly diagonal way, and then it fits. So one thing, like just I guess they say, like you don't argue with the Sicilian when death is on the line. You don't argue with the Russian when math is on the line. So so you definitely can't cheat. You cannot cheat the conductor. This is because he's Russian. And the question is, why not? So I love so let me say why, because this is like just so beautiful, because it comes out of nowhere, which is, suppose you could, say you had a box X inside another box Y. That means that the doodle around X, the dust cloud around X, this is where is contained in the dust cloud around Y. So in other words, if I were to have an imaginary dust cloud, now I'm using this fact from a long time ago that I told you I was going to use again. So that means this is inside that. So the doodle around the small guy is contained in the doodle around the big guy. Okay. So, so now I'm just going to write down, we know what we already worked out the size of the doodle, the volumes of the doodle. So the volume of the doodle of the small guy is less than or equal to, is smaller than the volume of the doodle around the big guy. And we worked that out, although I made a mistake at first, which is you have the volume of the doodle around the small guy is that, and the volume of the doodle around the big guy is that. And cancel culture is a big thing in mathematics, so I can't help but cancel these out. And now, what am I going to do? Well, now I'm going to let my doodle get really, really big, just like when I was 5 years old. Let R get really massive. And when R is really massive, these smaller terms don't matter. It's only the R squared term that matters. And that means that, now I can cancel these. That means the length plus width plus height of the big guy is at least as big as the length plus width plus height of the small guy. And the answer just fell right out. So it came out of nowhere, and I just don't, I love, I always it's like the unexpected chess move that just sort of suddenly devastates the opposition. Okay, so let me say one quick thing and then I'll conclude. The first is that if you've heard about Hilbert's problems, the famous problems at the start of the 20th century that were designed to lead to the, that he'd intended to guide the development of mathematics for the next century, the first one to get solved was one about dissection. The question was whether you could take a cube and cut it up into pieces and rearrange it to get a tetrahedron. So don't try this with these because these are mine, but you can imagine that if the volumes would have to be the same to have a chance of working. But it turns out that this is the first one to be done, and I'll just say it fairly quickly, that the reason you can't do it is because of this mystery new thing that's like volume and surface area that we mentioned. So when I say that there's this relative, this fourth sister out there that's important, she really is important in telling you something. So I want to conclude with a story because I feel like I should discuss something that I want to discuss something which relates to which sounds fancier and is fancier. So in dimension n, you get something similar, and now as the dimension gets bigger and bigger and bigger, you get more and more of these mystery terms. You have more and more strange sisters here, and these higher invariants you've got to believe are really important. So now I'm going to conclude with some links to fancier mathematics and things that so you can see that this is not just that these things, these metaphors really connect to how one thinks about really fancy things. So the setup is you have this notion of what are called Riemann surfaces. So I've just drew a picture of one that looks like this, and they have a certain number of holes, often called G for genus. And you may want to study what these things look like. They're things with shape, not just shape, but they're curved in certain ways. And so you might want to ask yourself, I want to study them. Is there a space of parameterizing all of them? And so Riemann knew somehow that there was a space called MG, the moduli space of these genus G things. He didn't know exactly what he was talking about, but he did know its dimension was 6G minus 6. So it was a weird thing that he couldn't even say what he was talking about. Like he really did not know. He could not say it's a space, but he knew its dimension. And so now comes the modern era, where so I should say the Fields Medal is like an award which is given to young mathematicians, and a good number of particularly brilliant mathematicians have won it. And it's harder than a Nobel. They give out an average of less than one per year. And so so David Mumford got a Fields Medal for creating, for really realizing making a name, figuring out what this space actually was and saying what it meant that it was a space. And then Pierre Delisle, a Belgian mathematician, also won a Fields Medal, not for this, but for things related to this at least, with Mumford, where they invented a new kind of space that better made sense of what this was. So that was another. And then a physicist, Ed Witten, who as a physicist is a better mathematician than almost any mathematician, was at the Institute for Advanced Study. And and at this point, there are lots of questions about the space. how big it was, what's its volume, what's its shape. And he had this conjecture out of nowhere called Witten's conjecture, where he told about the shape of the space and related to something really different. And I heard it described, I think by Mumford, that, and this is, I'm sure it's apocryphal, which is that Witten was like in his office, and God called him in his office, the institute, told him the conjecture, and hung up on him before he could ask any questions. So it came from string theory. It was very mysterious. Maxim Kontsevich, well, I should say Witten also got a Fields Medal, and then Maxim Kontsevich proved, a Russian mathematician gave a remarkable proof of Witten's conjecture, for which he won his Fields Medal. And a few years later, Andrei Kunkov and Rahul Pandarapande gave a second proof that was very different, very insightful. Kunkov got Fields Medal for this too. And I conclude with one more Fields Medalist, McMullen, who's here not because of what he did with this problem, but because of his irresponsibility as an advisor, a PhD advisor. He's also a Fields Medalist. So I'm going to end with the story of a graduate student who really, okay, so there are these questions about the shape of the space and the size of it. And the worst thing to do if you're a graduate student is to work on these problems, because the best minds of past generations have tried and failed to make any progress. So the story is about Mariam Mirzakhani, who, when she was a graduate student, decided to tackle these questions. And what she did, I should say her PhD thesis, like when you write a really great thesis in math, often it's going to get published in one of perhaps the top 3 journals in math. Her thesis was so good that it was cut up into 3 pieces, and each one went to a different one of the top 3 journals. And what she did is exactly what we've been talking about for this hour. What she said is she looked at the space and she said, okay, I want to understand this space. And the first thing she did is she said, I want to make the problem harder, so I'm going to cut holes in the space, so holes in my space of different sizes. And the advantage of doing that is now I have some numbers in the picture, and she thinks of them as doodles. So she has sizes where you have, well, she didn't use the word doodles at all, but where you have different sizes here. And so the size she was able to show is some magical polynomial, just like our area function. How did she find that it was a magic polynomial? She did it just like we did with the polygon, as you did when you explained how to construct it by dissecting it. She found out how to dissect this space in certain ways to give a recursion for this. And with this, she was able to figure out so there you go. She figured out the size of the space in a way that people could not before. And then what she did is, once you have the size of the doodle, we already know that like the leading coefficient, that like what you want to do with a doodle is like really small doodle looks like your original shape. So you do a really big doodle and you make it a big balloon animal like when you're 5 years old, and you see the most salient features of it, something really important. And it turns out that when she did that, it was exactly the terms that came out in Witten's conjecture, and then Witten's conjecture just fell apart because it just was like an obvious statement from her setup. And so really what she was doing is following exactly the same pattern. Not that she would say it this way by any means, but she certainly thought in this playful way. And so you really, that's how we think. That's how mathematicians think. And so just to conclude, I want to say that if you're willing to be curious, adventurous, and also fearless, and be willing to make wrong guesses, then you can find, just by asking questions about things out there in the world, lurking behind even simple-looking doodles, mathematics of rather amazing beauty and power. So thank you very much.
And as Ravi says, there's no such thing as a wrong question.
Yeah. Yes, question.
So you were dealing with boundaries. A while back, people were looking at fractals. Any relationship between what you were talking about and fractals?
Sure. So with boundaries, with boundaries, we had different behavior with different dimensions, and some of that polynomial. That polynomial, when you do your doodle, let me put it this way. Let me go back. When you do your doodle, you always have like the dimension turning up inside it. So you might say, like, here's a reasonable question, which you have something like that's a fractal, and you want to say, how would you define the dimension of something fractal, of a fractal? Someone draws a fractal. How will you make it up? And the question is, and you can imagine several ways of doing it, one of which is doodling in an appropriate sense, and another way is breaking it up into pieces in an appropriate sense. So I feel like the question is is the appropriate one to ask, which is you have something of dimension, of intermediate dimension. How do you make sense of something, that you can't picture, but is there in front of you? Like there's a
Another question? Good.
I had a question about the Russian box problem.
Yeah.
So to get the final conclusion that the lengths had to be greater, you had to take this kind of infinite limit.
Yeah.
So how are you sure that this would still work even in very?
Yeah. That's a good question. That's because I was carefully. Lying is an unkind word, but right. So you do have to be careful when taking that limit. So you have to. The way I would do it actually was I would divide everything by r squared, and so I was being deliberately cavalier, partially in the hopes that you wouldn't ask that question, but I'll. But more seriously, what I would do is I would look at this and I would make them go away by dividing both sides by, sorry, give me 1 second. Let's see, make a good color. I would divide both sides by r squared. Let's put everything back in the picture. Life is so much better with an iPad. Right, so I would, let's get rid of that. Great, and so I would divide both sides by r squared, and that would make this go away, and then these guys would become very small. And then I would have to make a limiting argument to say that these guys actually, when r gets really big, they kind of shrink away to nothing. So there is something missing. And so this is like the big picture, it's a big picture argument that's missing the last thing to make it precise. So I didn't even give a complete answer now, but I can say more later, but that's the. Although I really would say that the way I think about it is I always think the big picture personally first, and then I get precise later.
Yes.
Yeah.
As you were going through sort of the big picture, it seemed like your focus was on taking that radius and extending it out, which is the opposite of my intuition, which would be to take the original object and shrink it down to 0.
Yeah.
Do you lose anything by taking that approach?
No, except I would turn what you said on your head, which is I would call that doodling on the inside, right? You're shrinking it, and then you really are again still taking a limit. So like a really important thing. So an interesting thing then is if you do something like that, and you're saying you want to doodle on the inside, and then suddenly something interesting is going to happen when it runs into itself, and so there's like a really important common way of proving things in geometry is to do actually what you're doing, which is you have some shape you're trying to understand, and you want to break it up into smaller, simpler pieces. And so you change the geometry, because that's what you're really doing when you kind of deflate the balloon. And then something bad happens, and then either you throw up your hands or figure out to get around it, or you say, oh look, it broke it up into 2 pieces. I understand. So I agree with it, except I would. Say it as kind of the same thing. And the thing about letting R get really big, to me, is like a surprising thing as well. Because I feel like naively, I wanted to think of the small thing. And just repeatedly, in these things, you instead take this big thing and discover, it's like the small thing is like immediately visible. And the big thing is where interesting things happen. And that's true in your case, too. You're not taking a really small doodle. You're letting it keep on going until something interesting happens. And then you discover something.
Any other questions?
So from this formula, the coefficient of r to rk is only from n minus k dimensional information. It's not true for general.
In fact, it is true that you could do something like surface area. So which is not, this doesn't work for this argument, and I could give you, there's another trick for that in another country, okay, let's see. I don't want to. In country X, instead of doing length plus width plus height, they could do surface area. And actually, the same thing is true. You cannot fit a convex body of bigger surface area inside something of smaller surface area. So there are additional things that are kind of like this where the same argument doesn't work. So that's, again, the right question. Because once you see this happen, you ask the question of, you start to ask questions like what you just asked.
So
Yes, that's actually, you have to say that the right way, but that's actually true. That you can do something like this in general dimension, and then you're losing the information, the higher dimensional information, the higher, yeah. That's actually what you're saying is subtle but true, and that's actually how you end up figuring out what these invariants, these mystery invariants actually mean. I think I'm definitely not, I could talk more about it after, but you're completely right. But I think it's very non-obvious. I don't think it's so, yeah, I don't think that's an obvious statement at all.
I think we have another question. Jacob?
Does nature doodle? So when you look at a tree, when you look at the cross-section, you see these nice rings. And the tree is a nice cylinder, so it's circular. It seems like nature's doodling there. I'm just wondering if you have another example or if it's
Well, it's also true with waterways, right? I mean, I'm going to say something which is going to be obvious for people in other parts of mathematics who are present in this room. But even also water waves, if you think about water waves work, it's really like as ripples move. It's not really, you could say it's rippling out, or it's like each individual thing is like moving out little circles, and they all cancel out exactly to make a doodle that is moving that's moving forward at a constant speed. Yes, in a large sense, and yeah, I agree.
Yes.
Yeah.
These formulas you've got here are for lots. What if you started out with the tetrahedron?
Yes, so in that case, it's still true, but you need to know what length plus width plus height means. You need to define that mystery thing correctly. And I will even tell you what the answer is actually, because I've not, like the real way to actually say what the mystery thing is rather than length plus width plus height, you take your shape and you take a random shadow onto a line and work out what that random shadow is. That's that number up to something. So for a box, what it means to say is that strange. Let me say like a consequence of it, which rather than anything, rather than like if you take a unit cube, and if you were to take its shadow on the ground and work out its area, or its shadow on the z, like here, and take its length, you get the same number. That to me is not obvious at all. So yeah, we say unit cube, area, and length, same number. So when it's flat, it's 1, but when it's like tilted, that's not clear at all. But that's the thing to do with the tetrahedron, and then it's true. Then everything works. Yep, question?
I was wondering if, given the doodle and R, that you would recover the original shape, and also similarly, if the
Okay, that's a really super question. Your question is this a reversible process? Is information lost as you do this? Okay, yeah, that's and before I can even, maybe let me leave that as let me say that's a great question. And if you want to add some, like one clue might be would you go backwards? You might take his idea of doodling back inwards as well. And that should be potentially the way of inverting it. But maybe it goes wrong if they're dense. So then you start to, then I need to work through. Yeah, that's a great question. And once again, this is like this is like a prototype of a really important flavor of problem of you do something to make something better, or you have some process and you want to, and it makes it better, rounder, and you want to. The question is, are you losing information? Can you reverse time? Like knowing what's happened now, do you know what happened 5 minutes ago?
Any additional questions after what's great questions we had?
Yep.
Can you give us an estimate of the amount of fun you have giving talks like this?
Actually, the best part is when people say interesting things, like in terms of the ideas they have, because actually the amazing thing is that you might think that like the same questions. Actually, there have been 3 or 4 questions tonight that I've never heard before, and that are actually new ideas to me. So I feel this is like to me that's the most fun part for me, because I know what I'm going to say, but
This is a very nice part of doing mathematics, giving lectures, that the audience keeps us on our toes. So. Then no other questions. Well, thank you very much for coming, and let us thank our speaker again.
Thank you.
For beautiful talk. So thank you again, and hopefully we'll resume these lectures much more frequently in the future.
No more pandemics.